What's up, gamers? We are going to talk about free fall today. And this is exciting for a couple of reasons. One, because just by being in free fall, you get a ton of hidden free information. But you're thinking, oh no, what if I forget something? Don't worry. That's why I'm going to teach it to you. That way you've seen it before. Second, we're going to say a word for the first time today that is one of the most physicsy words that we're going to learn, and that we're going to base entire units on this word. So I'm excited for you to get to hear the word finally. And you're going to say, Barton, what's the word? And then I'm going to be like, bird. Bart is a word. Just kidding. I would never do that to you guys. That's so rude. Anyway, so let's talk about free fall. All right. The conditions for you to be in free fall. There's only one condition, and the condition has the word in it. The condition for free fall is that the only force acting on an object is gravity. And you're going to say, Barton, is the word gravity? Are we going to talk about gravity? Gravity is an important word in physics, but it is not the word. The word that is one of the most important words we'll ever learn in physics is force. So right now, we're going to keep this as intuitive and possible. Did I say impossible? I meant as possible. And we're not going to really define force. We're going to keep it nice and intuitive, and we're going to go with our gut on this one. So when I say the only force acting on an object is gravity, let's talk about things I mean that could goof that up. Some forces that might goof us up. Air resistance. And this one's a funny one because we're going to just straight up ignore this thing a whole lot. If I could draw quickly, I'd draw that like, you know what I mean? That like crying... like ha ha face guy. He's got like some real wavy hair. Like air resistance is one of the most ignored things in all of a introduction to physics course, and it's laughable how often we ignore it. So if the problem doesn't specifically say something that means there should be air resistance, like the wind is blowing, or the drag is, you know what I mean? If they don't specifically say something that tells you there has to be air resistance, we assume it's not there. And we can argue about like how safe of an assumption this is. Let me just describe to you why this is maybe a terrible idea, but we don't want to put it there if we don't have to. You can't really just ignore air resistance, right? It's a thing that happens often enough that engineers have to take an entire class on fluid dynamics because of it. Modern bicycles are something like 40% more efficient because they're shaped to deal with air resistance. And bicycles only go like 30 miles an hour. If you're good, right? If you're going fast, you're going 30 miles an hour, right? It matters, right? It matters if you're going up to like 15 miles an hour or down to anyway. That's when air resistance starts to kind of kick in and be important. So this is maybe not the best assumption in the world, but if you want to deal with air resistance properly, you have to take, it's like a 400 level undergraduate course where you have to do all kinds of calculus and differential equations and linear algebra and geometry, and then you have to build computer models, and you guys might want to do that someday, but we're not ready for that. So we're going to just ignore it and assume it's not there most of the time. Okay. The other things that could kind of goof up falling are, like the usual stuff. If you put rockets on something, if you put a parachute on it, if it whacks into some other object mid-flight, these could all goof it up. But it's pretty obvious. If you're just throwing a ball through the air, or you're falling out of a plane for the first 200 feet or so, ignore all this stuff. You probably don't have any of these things going on. All right, I'm glad we talked about it. So let's talk about the free information you get. Why is free fall so special, Mr. Barton? Why do we have an entire lesson just on free fall? So if we know something is in free fall, free information you get. There, I think, are going to be 4 things. I might have counted wrong, but I think there's 4. I'm only giving you 1 right now, and then we're going to discover the other 3. We're gonna calculate them and do some real physics to learn them and to prove to ourselves that they exist. The first one that you get for free is that acceleration is constant and equal to g. And we're saying lowercase g. This is a variable in physics. Or rather, sorry, I misspoke. It's not a variable. It's a constant. G is the symbol we're going to use for the acceleration due to gravity. So if you drop something, it's going to fall faster and faster and faster because gravity is pulling that thing downwards towards the Earth. Everything on the entire planet falls with the same acceleration unless there's air resistance. Trust me, it does. I'll make sure I link a cool video for you guys to watch to talk about this. But I can't put it in my video because, copyright and laws and all those other lame things. So lowercase g is going to be the symbol we use to represent the acceleration due to gravity. So this is an acceleration. And you're saying, Mr. Barton, tell me what it is. The acceleration is 9.81 meters per second squared downwards. Or more technically, towards the center of the Earth. But in general, we're not looking at things big enough to really matter about that. And we just say, down. However, this number is not that great for us doing mental arithmetic. So in this class, and on the AP test, they're totally okay with you doing this on the AP test. We are going to round this thing to 10 meters per second squared. This is the one you should use if you're doing rockets and space flight and airplanes and things like that in the future when you're an engineer. This is what we're going to use in high school physics class because it's easy to multiply and divide by 10. And if you feel like a little dirty because of this, is you feel like you are cheating mathematics and you're saying, we can't do that. I'll get the wrong answer. This number is too different from the regular answer. Let me tell you an allegory. I once had a professor. His name was Professor Schmidt. I think that's how you spell it. And he was my quantum professor. He taught me quantum mechanics 1, which is like the very first class you take on quantum mechanics. And I once watched this man approximate a molecule, or an atom, rather. This was a big atom, too. This atom had something like 83 electrons. He then approximated this down to 1. So when I say that we're going to approximate 9.81 meters per second squared to 10, and you think that's bad, I saw a guy approximate 83 as 1 before and say it was fine. So I don't feel that bad about it. Maybe I'll tell you guys a joke tomorrow. or today, rather. Maybe I've already told you the joke. That would be funny. If you, if looking at your left hand is funny to you, then maybe I've already told you the joke. If not, ask me about it. All right. So this is our first free piece of information. If you are in free fall, the acceleration is g, and g is 10 meters per second squared down. And that's what you need to know to get us started. We're going to come back and fill these in, but let's go do some physics first. All right. So I like to learn physics by looking at real life scenarios and then seeing what happens, because that's kind of how physics works, is physicists measure an experiment, record some data, see what happens, and then they build their math on top of these observations. So what we're going to do is we're going to look at a situation that you're probably pretty familiar with. If you're not familiar with tossing something straight up and having it fall down, go grab your mom's nicest piece of glassware and go out back and toss it up and catch it. And see how long it takes her to freak out. Or alternatively, a ball or, something else. But we're going to look at this example. So the first question we want to ask is, what happens at the top? And when I say the top, what I mean is we've got our girl. What do girls look like? See, the problem is girls can look like whatever they want to look like. So I want my girl, talking about my girl's got some pink hair. Because she skates. That's how you could tell she skates, because she's got pink hair. How about that? That's some... Dang, girl, you looking cute today. All right, cool. Don't tell my wife. All right, so this girl takes this tennis ball, because I like tennis. And she's going to throw the tennis ball up, and the initial velocity is going to be 15 meters per second. Okay. What happens when you throw a ball up? When you throw a ball up, is this one ball? Yeah, nice. Sometimes this doesn't group right. When you throw a ball up, it goes up, it slows down, and then it falls back down. And then you catch it, and it's super sweet, and you're like, Mom, look what I can do, right? So let's talk about a couple of things. Let's start by looking at a qualitative graph of the position of our ball. So I'm going to make a little graph here. Okay, and this is position. We'll measure it in meters. This is time, measured in seconds. Okay, so this girl, she throws the ball up. So when we start, the ball is going to have some initial velocity. I'm gonna define, because I'm a physicist and I can pick whatever I want. Her hand is x equals 0, because I don't want to deal with negatives, and you know what I mean. So she's gonna start at 0. Her initial velocity is 10 meters per second, or 15 meters per second, and the acceleration, let's make that yellow, is 10 meters per second squared downwards. Okay, so she's going to throw up the ball. It's going to be moving at 15 meters per second. It starts at 0. Let's start graphing. Let's do teal. So initial position is 0. The initial velocity is positive 15. So this should have a positive slope to begin with, like that. So it's going to be going up. After 1 second, it's gone some distance up. It was going 15 meters per second. Now, after 1 second, we've lost 10 meters per second. Because this is down, we would say that this is negative, because I'm saying up is the positive direction, down is the negative direction. So it had 15, we lost 10 this second, so now it's just going 5. So it's still going up, but the slope is a little more gradual now. Okay. After half a second, if I lose 10 meters per second, after half a second, I'll lose 5 meters per second. So it goes for another half a second And then the velocity is 0. What does the velocity of 0 mean? What that means is that our slope is horizontal for our position graph, and the ball has stopped. Then time continues on. Our acceleration still acts on the ball. So let's go another half a second. Now it's going negative 5 meters per second. So now it curves back down. And then after another second, it's going 15 meters per second. It falls back down, and it's a little more steep. So what we get is a projectile that looks like this. And if we actually look at our displacement equation, displacement final equals 1/2 times our acceleration of negative 10 t squared plus initial velocity times t plus initial displacement, which is 0, so we'll just omit that. Okay. Because we have a t squared here, this shape is actually a parabola. Let's label that parabola. Okay, so at the top of my position, when I'm at the max height, what happens to my velocity? Velocity equals 0 at max height. Okay, so that is one of the free pieces of information that we get that we should add to this list. That's a very important fact that you want to remember for the rest of your life. The way you remember that, my recommendation is that if you're 18, you go and get a tattoo of it, and then make sure you show your parents. They will love it, I promise. If you're not 18, walk up to your mom or your dad or whoever you think is more likely to say yes. Hand them the permission slip for the tattoo and tell them it's a field trip form. And say, Mom, I need you to sign this so I can go on a field trip to Castles and Coasters. Or better yet, the library. Mom, we're going to the library. Can you please sign this? And then go get the tattoo. And then you'll never forget it. Because if you do, you can just look at your arm or your wrist or your bicep or wherever it is you get it. Make sure you get somewhere that you can see. So lower back is probably not a good place for this. Inner lip, probably not a good idea. Somewhere you can see. So the piece of information we get for free is at the top, at the max height, velocity equals 0 meters per second. Okay, we're going to be able to use this piece of information to solve for a lot of stuff very quickly because we can just assume this. And we're not assuming it. We've kind of proved it by looking at this graph and looking at the slope of our displacement graph and doing some quick maths in our head with this stuff. So what happens at the top? How fast is it, meaning our tennis ball, going at the top? 0 meters per second. Cool. All right. Let's talk about how long does it take to come down. So let's look at an equation, shall we? This might be the hard question. Let's skip it and let's look at this one first. Okay. No, we got to look at this one. We've got to look at this one. Okay. So we've got the same setup. Let me reset this up. Copy. Let's go here. Paste. Okay. So the girl tosses the ball straight up into the air at 15 meters per second. How long does it take the ball to fall back down and for her to catch it? Okay. So what we're going to do is a sneaky physics trick, and we're going to break the problem up. We're going to look at the time it takes to go up. So we'll put T up. And then we're going to look at the time it takes to come down. So T down. And then we're just going to add these two times together because time up plus time down should be the total time to go up and come back down, right? Makes sense to me. So the reason we're splitting this up is because doing this single problem, if I want to do it all at once, what you have to do, and you could do this, if you want to do it the hard way, be my guest. But I'm going to show you some tricks. What you would have to do it the hard way is look at your quadratic, negative 10 t squared plus 15t. And then you would need to simplify this thing and factor it. Actually, that's not that hard. Let's go ahead and do it. Let's look at some options. Then we can come back and look at this because it's always good to know how you do it two different ways, right? So let's simplify first. X final equals 1/2 times negative 10 will be negative 5 t squared plus 15t. All right. If the ball goes all the way up and then comes back down, what is the final position if it's back in her hand after it's fallen and she's caught it? Meaning, if we're looking at our position time graph, which is this really nice looking parabola, we're looking for this root right here, the 0 for the parabola, where it intersects the x-axis. So our position would be 0, right? So we're going to set this equal to 0. And now you're having flashbacks to Algebra 2 class where you had to solve this, which is actually pretty easy. So we could factor out the GCF of t. So we have 0 equals negative 5. Let's factor out negative 5t. So we take out negative 5t. So this is now t minus 3. Okay. So one of our roots is t equals 0 right here. What that means is at time 0, the ball is at position 0. It's in her hand. So all this answer is telling us is before she throws the ball is in her hand, which is good. We want it to say that because otherwise we'd have some questions, right? Where else would the ball be if not in her hand? Okay, I'm just feeling like my pens were the wrong size. The other one is this right here. So we set this equal to 0 because 0 times anything equals 0, and that would be a solution. So t minus 3 equals 0. Add the 3 over. T equals 3 seconds. Okay, so this is nice. We've solved the problem. How long does it take the ball to fall back down? But let's look at it broken up, because the broken up part, there's a special relationship between this time and this time that is going to go on this list. Okay, so that's all well and good. You have to solve a quadratic, which is maybe a little intimidating for people, but you know, c'est la vie. That's life, kid. We didn't teach you how to solve quadratics in algebra for nothing. So let's do the easier problem. Let's find the time to get to the top. Okay. So we have, if we want to know how far it goes to the top, let's look at the displacement equation and talk about why that's a bad idea. So x final equals x initial plus velocity initial time plus 1/2 a t squared. Initial position is 0. Final position, we don't know that. Okay, that kind of stinks. Initial velocity is 15. A is negative 10. And time, we don't know either. So if we make our substitutions, x final equals 15t minus negative 5 times 10 would be, or negative 10 times a half would be negative 5. So minus 5t squared, right? This equation right here. The problem with trying to use the displacement equation here is that we have two variables. We don't know how long it takes to get to the top, and we don't know where the top is at. Okay, that kind of stinks. So this is not going to work for us. Okay, so we'll abandon that idea. We tried it, we plugged some stuff in, and we said, the fundamental theorem of algebra is in our way. We can't solve for two variables with one equation. It just doesn't work. So what we're going to do is abandon this thought, And we're going to try the only other like real big kid equation we know. Let's look at the velocity equation. V final equals acceleration times time plus V initial. All right. The final velocity, or the velocity at the top, well, that's the thing we just learned on this page. V equals 0 at maximum height. All right, cool. So our final velocity is 0. Our acceleration is -10. Our time is what we're looking for, and our initial velocity is 15. So if we plug all these in, we have 0 equals -10t plus 15. And this is an even easier problem to solve than this up here because it's not a quadratic. So let's solve it. Subtract 15 on both sides. So we have -15 equals -10t. Divide by -10. And we have positive 1.5t. Awesome. So it takes 1.5 seconds to get to the top. So we've just figured out our time up, 1.5 seconds. All right, now the brilliant of you can infer if the total time is 3 seconds and it takes 1.5 to go up, it has to take 1.5 to come back down. Okay, you're right, that's correct. Let's see how we would set this up just to really prove it to ourselves so that we're not assuming things. Because sometimes when you're learning physics, you make wrong assumptions, so we want to just double check. So now what we're going to do is we're going to look at the time down. Now what we're going to do is going to say we start at the top. So V initial for this half of the problem is 0 because we're going 0 meters per second at the beginning. Oh no, this actually isn't. We're going to learn something in a second here. It's on the next slide. I just realized that this problem's not going to work all the way through because we don't know how fast it's going at the bottom. You can probably guess, but we don't know for certain. Okay, let's just go with this, and then we'll figure this out on the next slide. So this will always be true. The time up will always equal the time down, star, unless there's air resistance. So we have figured out by doing a little bit of math, one quadratic, one linear. I know, I'm sorry, I'll get you a tissue. That the time it takes for something to go up in free fall equals the amount of time it takes to come back down in free fall. So let's add that to our important stuff we know. Time up equals time down as long as there's no air resistance. Oops, air doesn't have an E. Cool. Super nice. This is very handy. You're welcome. All right, now let's answer this question. Is how fast is it going when it comes back down? How fast is the ball going when the girl catches it? So, please still, heck yeah. All right. So we've found out so far that the time up equals the time down. Okay. And now let's use this information here to calculate the velocity at the bottom. We're looking for how fast, so we're going to use our velocity equation because that seems prudent. V final equals V initial plus acceleration times time. It also equals acceleration times time plus V initial. I apologize if I'm confusing you guys a little by kind of ambiguously switching back and forth between these. Sorry. I don't know. All right. So let's look at this half of the problem. Okay. We know at the top from our first example that V at the top equals 0. We're going to make this the initial part of the problem because we're only looking at this part. So it starts with the ball at the top and ends with the ball at the bottom. So this is initial, and this is final. Okay. We don't know how fast it's going at the bottom, though you can probably guess. Acceleration is constant because we're in free fall. So this is still negative 10 meters per second squared. And we already calculated that this time is 1.5 seconds because time up equals time down, and we did the math on the last slide. So let's just plug our numbers in. So we have V final, the V at the bottom is a question mark. V initial is 0, so we'll just get rid of that. And our acceleration times our time, so negative 10 times 1.5. V final equals negative 15 meters per second. All right, let's compare that to the initial velocity. It's the same number. They're both 15, but this one's negative. What do positives and negatives indicate in physics? Direction. So the only difference here is that this ball is going down and this ball is going up. But they have the same speed or magnitude, same number. So what we've learned from this example is that V up equals negative V down. Meaning when you throw anything into projectile motion, the velocity right here equals the velocity right here, but in the other direction. The velocity right here, a little lower, a little smaller, is equal to the velocity right here, going that direction. So the slope of a position time graph here is equal to the slope here, just this side's negative, because parabolas are symmetric, which kind of makes sense. So this is what we are learning from this last chunk of this problem. Okay, so let's go write that down. V up equals negative V down. And we might want to elaborate a little on what this equation means. The velocity of an object going up is the same speed as when it's coming down. When the heights are the same. So if you know the velocity while it's going up at any height, so it's halfway up, it's at whatever height it is, and you know it's going 5 meters per second, after it goes all the way up, stops and starts to fall, when it gets to that same height again, it will be going the same speed, but in the opposite direction. Cool. And these are the 4 facts about free fall that you need to know. The acceleration is constant, and it's always equal to g. On Earth, g is 9.81 meters per second squared downwards, or for this class, 10 meters per second squared downwards. On other planets, it's a little different. At the max height, v is 0 meters per second. So when something gets to the highest point, it stops, and then it starts to fall back down. It takes the same time for it to go up as it does to come back down. So if you know it takes something 14 seconds to go all the way up and then come back down, you know it took 7 seconds to reach the max height and 7 more seconds to fall back down. And then you also know if something is going up at 5 meters per second, once it gets to the height, starts to fall back down. Once it gets back to that same height, it'll also be going 5 meters per second, but down this time. And those are the 4 things you need to know. All right. So that's a lot of math and a lot of stuff. Let's go apply some of this to a practice problem. Sorry for that blinding white screen. So this is going to be a fun one. We might not use every piece of information here, but it's a fun one just to help you pick out variables and show you how to solve problems like on your homework. So a pigeon is sitting on the roof of the Capitol building and waiting to poop on unsuspecting people as they walk out. The support the pigeon is sitting on is 8 meters high, and the average politician is 1.5 meters tall. How long does it take the poop to fall on their head? How fast is the poop going when it hits their head? Okay, awesome. So here we have the Capitol building, some non-partisan politician. You can see he's wearing red and blue, so both Democrat and Republican. Any resemblance to past politicians is merely a coincidence in this case. No offense is meant to anyone. It's purely coincidence. This could be any politician, honestly. So let's figure out, what are we looking for? How long does it take? That sounds like we're looking for some time. For the poop to fall on their head. How fast? This could be speed or velocity. We'll say velocity just to be safe. Was it going when it hit their head? Okay. So if we're looking for a velocity, we're probably going to need the velocity equation. And this has a time in it, but maybe we won't be able to solve for that yet. Maybe because it does tell us some distances here. That's kind of a hint that we might also need our displacement equation for this problem. So let's write them both down just so we are kind of aware of both of them and we're picking out important variables. Okay, so it says a pigeon is on the roof of the Capitol building waiting to poop, blah, blah, blah. The support the pigeon is sitting on is 8 meters high. So the height of this pigeon to the ground, this is 8 meters. That looks like where the poop would start, assuming poop comes out of pigeons. So we're going to say our initial position, we'll say that that's 8 meters. By doing this, we're saying that the ground is x equals 0, and this is x equals 8, and we'll say that up is the positive direction. Okay. The average politician is 1.5 meters tall. So the top of this guy's head, this is going to be 1.5 meters tall. The poop is going to end on the head of the politician. Oh, it's locked up. Okay, I can't move the poop. Apologies. You won't get the satisfaction of seeing it happen, but I'll let you imagine it. So if it ends on his head or her, this could be a woman. Any resemblance is coincidence. Then this is going to be the resting place or the ending of the problem. So we're going to say our final position, x final, equals 1.5 meters. All right. That looks like all the information they tell us. So we're going to have to use some of the stuff that we learned from the rest of the lecture, and we're going to have to make some assumptions, which is often the case in a physics problem, but that's okay. So is the poop accelerating? Will the poop speed up as it falls down? Yes, of course. The poop is in free fall. So that tells us the acceleration. Our acceleration in this case is 10 meters per second squared downwards. Because it's downwards, we're going to make it negative. Okay. So I have the final position. I have the initial position. I have the acceleration. We're looking for time. Do I know the initial velocity? We don't. So unfortunately, we're going to have to make an assumption here. And it might be good to write it down. Hey, I'm assuming this because it's not given to us anywhere. I'll be honest with you. I have not studied the motion of pigeon poops very carefully. I know that some animals are known to projectile poop, and they get some real velocity on that thing. But for simplicity's sake, we'll pretend that this pigeon had a pretty solid poop and didn't have a lot of back pressure in its bowel system. So we'll say that it just drops the poop. And we'll say that the initial velocity is 0 meters per second for simplicity. If a biologist would like to send me an email and tell me the actual initial velocity of pigeon poop, that'd be great. But until then, we're going to assume pigeons poop similar to humans, and it kind of just gently falls out without any real oomph behind it. So at least, anyway, that's how mine works. So, all right. So now we're ready to solve a problem. All right. We know initial velocity is 0. So that's 0. This whole term goes away, making the problem a lot easier, hopefully. It looks like I don't have enough information to solve this question yet because v final, that's a question mark. We don't know how fast it's going. And time is also a question mark. So we have 2 unknowns, and this equation isn't strong enough to solve 2 variables by itself. So we're going to have to make a pit stop and maybe try this equation first. So final height, we know that. It's 1.5 meters. Initial, well, it starts up here at the pigeon at 8. This is 0, so that goes away. And we know 1/2 an a. That'll let us solve for time. So plus 1/2 times -10 times t. The physics is done here. You have finished all the physics. We are now doing mathematics. Okay, you're an accomplished physicist. If you were a doctoral physicist, you were a researcher, you would take this, hand it to some unfortunate undergrad, and say, "You do the math for me. It's not worth my time." Unfortunately, you're a high school student, so you have to do all the hard work yourself. So let's solve this for t. Simplify 1/2 times -10. That's -5t. So now we're going to just solve. So subtract 8. These cancel. This is -6.5 equals -5t. Then we take our calculator and divide by -5. So t equals... Don't tell me. I want to find out. Is it 1.2? I think it is. Let's just double check though. But 1.3. 1.3 seconds. All right. We now have our time. It takes 1.3 seconds for this poop to fall on this poor soul who totally doesn't deserve to be pooped on. But c'est la vie. Pigeons are indiscriminate poopers. Now we know the time. So this is no longer an unknown, and now we can utilize the velocity equation to solve for the final velocity. So let's switch colors again. Let's go, how about green? All right, v final, that's a question mark, equals v initial 0, acceleration is -10, and time is 1.3. We multiply. V final equals -13 meters per second. This is approximately, I want to say like 27 miles per hour, I think. I'm guesstimating here. Negative, meaning just downwards, of course. So, that's a pretty quick poop. So, this poor guy, we'll call him Toronto Dump, because he's getting dumped on. Gets pooped on at -13 meters per second. All right, and there we go. That's how you solve physics. Just a quick 44-minute video. Hopefully it was enjoyable. Hopefully we had some laughs. Please don't tell your parents. And until next time, happy physicsing.